there quite often. See Wood and the guys. I know them quite well. Trevor.
So they're a good group of guys then? I picked a good
Yeah,
place?
yeah, they are. They've been around for a long time. Just trying to think of the engineer I deal with sometimes. It's next to Randall's office. It'll come to me
Like
right away.
Colin McIvory or something like that?
There's Colin, and then there's the other guy. Kalen, I should say.
Oh, yeah, Colin.
Kalen, and then what's his name? The guy, the office next to him, right in the corner there.
Oh, honestly, I've never been there yet. It's all been virtual, so.
Oh, you haven't worked with Wood at all yet? Like no co-ops,
Nope.
no nothing like that?
Nope.
Oh, okay, very good. So you must have just got the job because I think they were advertising just recently. Is that correct?
Correct.
Yeah. Okay. Well, that's good. That's good. The rest of you, if you guys are members of LinkedIn, they have a career section, and if you go into the job opportunities with LinkedIn and click, construction and civil engineering, and go across Canada, there's numerous all over. Now, some of you may not be able to relocate, but those that can, I mean, there's work from BC right to Newfoundland. From what I've seen, I kind of track it and let the students know it's available, but Ontario, BC, even Wood has numerous positions across Western Canada. So it's something to keep in mind is check into LinkedIn careers or job opportunities. There's lots on there. And you can filter what you're looking for. You can filter the region, you can filter the province. You can even go international if you want. Anyhow, okay. I'll get the recording going here right away. We might as well get started. Come on.
John?
Yes.
Were we supposed to change the specific gravity for the lab or just use the ones that you provided?
No, you got to use the ones that you've determined from your other labs.
Okay.
Okay. Okay, my video is not starting here for some reason.
Hey, John.
Yes, sir.
One other question. So for that first lab, we did a written report. Was that something that we just did for that first one, or were we going to be doing that for other ones too?
We're going to be doing it for other ones too, but with the data, I mean, you can always write a summary as such if you want what you're doing. But when I see your spreadsheet, or when I guess what I'm getting at is a lot of this data then is going to be used when you write up your last report, which is going to be coming up in the next lab, where we're going to do a compressive strength and a flexible strength test. And I'll explain more of that in the next hour when we do the lab. Then you're going to summarize your data because you're going to determine your compressive strength and your flexural strength. I will give you some data that you would typically generate yourself. It's imperative that those two videos for the structural test, for the compressive test and the flexural strength, you have to witness, because it goes into a lot of detail as to how the structural, why am I always saying structural? How the flexural and compressive strengths are done. When I give you some of that data, then you're going to be using that data to calculate the compressive strength, the flexural strength, and then you're going to write a letter report giving me the 7-day strength, the 28-day strength, and so forth. I could have asked you guys to write letters for these last 3 labs, but I thought, you got your plates full already. I mean, if you want me to ask for technical letter reports, I will, but I'm just trying to understand that I know you guys are swamped. And sometimes letter writing takes a little bit of time and effort. In fact, it does take time and effort. It's not easy. But your last lab report will be written up in a technical letter format.
Hey, John.
Yes, sir.
Yeah, for the specific gravity, I was referring to the cement and fly ash, not the aggregates that we had.
Oh yeah. Typically, and we're going to be covering that shortly here in the cement lectures here. 3.15 is used in the industry quite often. I mean, it varies anywhere from 2.9 and up. But we use the average, and most call it designers, or most people use 3.15. That's typical for GU Portland cement. Same with fly ash. Fly ash varies from 1.9 to 2.8. I just took the average, 2.35. Some use 2.2, some use on the higher end.
So it's okay if it is similar.
Yeah, so as far as your aggregate GSs, you use what you determined. For
Yeah.
the cement and the fly ash, we'll just use what the industry is using because we've never run any tests on cement or fly ash.
Yeah, okay. And what about the formatting of the lab? Is it okay if we use the example you gave?
Well, I've noticed some have. To me, that's a lot of, well, it doesn't get you guys thinking how to set things up. I was always reluctant to give PDF copies because sometimes people take it word for word. If you want to use it, go ahead. Some people have used it. Some have set up their own presentation, their own layout or format. If you want to use it, go ahead. But it doesn't get you guys thinking much as to how to set things up. You're going to be involved in industry writing reports. You have to start right from scratch. Now's the time to start thinking of how to present data. Use what I gave you as an example, but I mean, if you use it, you use it. If I didn't want you to really use it, I wouldn't have put it up. I would have said, make your own, but I'm easy on you guys this year, but that to me stifles your creative thinking. Does that answer that?
Yeah, thanks.
Okay. That's the same with the letter report. For the most part, we're good, but I noticed some groups almost copied my letter report word for word. Okay. I've always suggested go back to your technical communications and what you learned there as far as letter writing. I'm sure you covered that in your technical communications, how to set up a technical letter report, how to address the salutation, how to use a subject line, how to close it, where your signatures go. Okay? Anyhow, okay, let's get recording here and okay. Let me just set it up here. Come on. Okay. You guys notice the email where I've extended the due time for the lab till 10 o'clock from 6 o'clock? Okay. The reason I've done 6 o'clock, like I explained in my email, was the fact that, get it over with and then you have your supper and you set. I thought some may want a little bit more additional time, maybe you'll grab supper and get back onto your computer. So I've extended it to 10 o'clock now for the remaining labs that we're going to be doing into asphalt and so forth. So if you have any questions about that, let me know. Another general comment, and I could have brought it up in the lobby, but I'll bring it up now. Please, if there's any issues with the groups that you're working in, I know you may have set up some of your groups from last year, but again, lab work is a group effort, and I've always found out after the fact, almost close to graduation time or final exam times, when one lab group says so-and-so hasn't been pulling their weight, so-and-so hasn't been pulling their weight. The time to nip it in the bud is right off the bat. If you've experienced this in lab 1 and lab 2, resolve it. When somebody's riding on the coattails of somebody else and getting the same mark, and if they're not pulling their weight, typically it's not fair to the other individuals. So if you have a problem, you can't resolve it, send me an email, excuse me, and I'll look into it. But other than that, keep that in mind. Report writing, data analysis, setting up spreadsheets, whatever the case may be, is a group effort. Okay? Don't let one person do all the work and the other two reap the benefits. Okay. Okay. Any other questions or comments you guys have you want to do?
Do you know when you'll have the marks out for the quiz?
I'm just about finished. I should have them, hopefully. I thought I was going to have them by today, but I kind of watched a couple of hockey games and curling on the weekend. Slapped my wrist. I was a bad guy. Anyhow, so I'll try and get them finished up today and hopefully have them posted and returned tomorrow sometime. For the most part, you guys are doing well. A couple are borderline, but anyhow, other than that, for the most part, not bad. Okay, I think there's even a perfect paper. So that obviously I didn't make the quiz hard enough. So if somebody's scoring perfectly, then I gotta make it tougher. You only learn better that way, right? God, nobody agrees with me? What's going on here? Okay. No thanks. What's the matter, Kelly? Remember, nobody likes a coward. Okay, enough said. I'm going to share, we're going to cover a couple, 4 units actually, which is quite a bit. But we have to, if we're going to stay on track. And I've reduced them quite a bit. I've highlighted some key areas. The important parts, I will continue to highlight if I notice something that's been highlighted. So you guys can highlight on your own as I'm doing it. And we'll take it from there. So we're going to be looking at cements. We're going to be looking at mixing water. We're going to be looking at the admixtures. And one of the most common SCM, supplementary cementing material, which you guys are aware of because you used it in your mix design, and fly ash. Fly ash can be a science in itself. There's numerous papers and textbooks and research done on fly ash. Obviously, we're just going to cover some key highlights of it. But let's get started here. We'll get going on cements, because cement, again, is one of the key ingredients, obviously, in the concrete. So let me just share something up here on your screen. Oh, come back here. I'm going to chat out here so I can see if somebody's got questions here. Okay, Portland cement. Does anybody know why it's called Portland? How did this name come about? Portland cement. Portland, England, the island of Portland. You're right. Joseph Aspen, a chemist, first came up with it, and because it was the color of limestone from the island of Portland, he decided to call it Portland cement. Anyhow, just a name. Okay, Unit 3, we're going to look into this. Again, there's a little bit of history on it. Don't worry, I don't quiz you on the history. It's just something nice to know. When you buy a bag of Portland cement at Home Depot or wherever the case may be, Lowe's here in Canada, it's 40 kilos. Typically, a bag, US bag before we went metric was 94 pounds. Now we're 40 kilograms or 88 pounds, okay? Now, we have Portland cements, which are manufactured, and we have natural cements. And natural cements have been used in the past. However, for our purposes, for construction and for engineering, it's not recommended, very undesirable. It's too, what's the word I'm thinking of? Uncontrollable. You don't know what to expect. It's kind of a hit and miss. So in construction, you got to be careful because you're going to be relying on finishing, you're going to be relying on workability, and the initial set, natural cement set up way too fast for us. Now, even with our Portland cements, we can retard the set. And when we look into admixtures, we'll be looking at retarders. So again, natural cement is undesirable. It's unpredictable, okay? You can see the specific gravity of it is quite a bit less. We're on the lower end of ours. We're at 3.15, it's about 2.93, okay? The final set is usually attained within 10 hours. Ours can be around that also. We can start cutting concrete pavements anywhere between, with the GU cements, anywhere between 5.5 to 6 hours, which means it's not final set, but it's setting up enough to support weight. But the initial setting time, 10 to 20 minutes, that's fast, okay? You're going to lose your plasticity. You're going to lose your workability. So again, natural cements are not ideal. Again, natural cement should not be used exposed to structures, water, marine environments, not resistant to salt attack as much as our normal Portlands, because we can manufacture, we can change composition of ingredients in various cements. That's why we're going to have 6 types of cement. Okay, in Canada, we have 6 various types. And by changing raw materials, we can change the composition of the cement, make one more resistant to sulfate attack, make one less heat of hydration, in other words, not producing as much heat. Okay? Portland cement, hydraulic. What that means is it means that it reacts with the water. It's fluid. And when it reacts with the water, we undergo a chemical reaction. And that chemical reaction is called hydration. Okay? Very common term on quizzes, very common term on exams. Okay, the chemical reaction between the cement and water is called hydration. And that's what gives you, that chemical reaction creates a hardening process. That's why concrete sets up. Here again is the chemical reaction of it. I don't quiz you on it. I don't want to really know myself other than the basics. But my chemistry goes back to grade 12, so I might have forgotten a couple of things. Okay. Very definite proportions, okay, are maintained for the various types. So if we're going to make 6 types of cement, 6 different types, we're going to change the proportions of the ingredients. Now, cement is manufactured from raw materials, so we have to find the raw materials that we need to produce this design and control of concrete mixtures. If you guys are going to be working for some of the consultants, they may even have this in their library. This is the textbook that we would have been using this year. Okay, chapter 9 came from it, from an older version from the Portland Cement Association. We were using one that was donated by the Concrete Ready Mix. It's the 8th edition, the Canadian edition, by the Cement Association of Canada. So in there, there's a real good unit on cement and manufacturing, raw materials, where to find them, and so forth. If you get a chance to get a copy of that manual, by all means, take a good look at it. Okay, we're going to look at the key. These are the natural cements and Portland cements. Again, this is just for your interest. I'm not going to quiz you on it, but it gives you the raw material, basically where Portland cement gets them. Okay. Now, so we have a standard for concrete, CSA A23.1 and A23.2, which you guys are using now from the library. There's also one by CSA for cement, strictly cements, okay, Portland cements. And it's CSA, it's a compendium, as they call it, A3001-08. And it's been developed by CSA. So there is one if you're working in the cement industry, you're working for a manufacturer of cement, whether it's Lehigh, Folsom, Lafarge, Canada Cement, Hudson, St. Mary's, whatever the case may be, they have to follow CSA standards for cements to ensure their cements are meeting standards. Okay, what do we make cement out of? Well, we need some raw materials: calcium, iron, silica, and alumina. Not aluminum, alumina. And these are obtained from raw materials. Okay, limestone. There's a video set up in the lecture notes here on the manufacture of cements. I believe it's Exshaw, one of the biggest producers of cement in Alberta. It's a pretty good video. It tells you the manufacturing process. I do suggest you review it, because when I'm talking about kilns and I'm talking about temperatures, when I'm talking about clinker, it may seem pretty Greek to you, but the video ties everything together. So first of all, you're going to have a quarry. You got to find a quarry to bring in your raw materials. And the raw material is going to be processed. It's going to be crushed. It's going to be heated to phenomenal temperatures. Okay? So the raw materials that we need to manufacture Portland cement are calcium, iron, silica, and aluminum. The powdered mix here used in the manufacture of Portland cement are initially crushed, mixed together in the proper proportions, and then ground to a very fine powder. The powdered mixture, either in dry form, which is what most use, okay, is fed into a kiln, almost like the kiln that you use to heat asphalt aggregates. Phenomenal temperatures, you're going to add the asphalt cement on one end of it, and it's going to get mixed and heated, then it goes up. Here we're just basically heating the aggregate with phenomenal temperatures, then it undergoes a change. Such high temperatures is going to change those raw materials. The raw mix passes through the kiln at a rate controlled by the incline, the slope, okay? Because the aggregates are going to go from one end of the kiln to the other as it's being heated. If you want it to go through quicker, you give it more of an incline, the aggregate's going to fall quicker. If you want it less, so they can adjust the incline of the kiln, 1400 to 1500 degrees C. So you're going to do a chemical change of the ingredients. Here's the key part now. This is the last stage, essentially, where you're going to get Portland cement. When you have a chemical change, you're going to get brown pellets. And these pellets are known as cement clinker. It's undergoing to go another final grinding, which gives you your powdered cement. Okay? Chemically changes the raw material into cement clinker, grayish black pellets, about 20 millimeters in diameter. So they're not very large, but 3/4 of an inch. Now, one more thing we got to do here. As the clinker is cooled and pulverized, you're grinding it, small amounts of gypsum, 4 to 5%, is added to the clinker. And the reason for that is you want to regulate the setting time of the cement. You also want to develop early strength gain. And you're going to improve its shrinkage. Okay? And you're going to increase, or you're going to improve the strength developments. So that's key. Know that. Okay? Why do we add gypsum to the cement clinker? Regulate the setting time, develop early strength, improve the shrinkage, and also improve the strength developments. So without it, your setting time cannot be regulated. It might set up way too fast. And again, this is where we can make the different cements. You're going to have high early cement, HE cement, which we'll look into it later. And that develops strength a lot quicker than Portland, the normal Portland, GU, for example. Okay, so you can see how we can adjust the various properties by using clinker in our cement, and it's got to be controlled. And we look at Portland cement average specific gravity 3.15. That's typically what we use. Okay, any questions so far? Initial set. What is initial set? Many times you guys that are involved maybe in concrete testing, the contractor gets a load of concrete and starts to set up really quick. Hey, initial set is kicking in. Maybe the distance, the travel time was too long. And already, once water and cement come to play together, okay, the water can come just from the aggregates. So in other words, you may have damp aggregates, drop them onto a scale, add the cement powder at the batch plant. Well, that cement and water has not come together. Hydration is starting, even though you may not have added mixing water. Okay, so that's when set is going to be starting from. The initial set is going to start from the time it comes together. So you might get an initial set in 2 hours. You may get it in 1 hour. Okay, so when does the hydration start taking place? As soon as water and cement come to play. And the water can just come in from the aggregates. That's why if you store bags of cement in your garage or your workshop, make sure it's off the floor. Make sure the bags are not going to get, subjected to moisture, because it'll start to hydrate. Your cement will start setting up in the bag. That's different than dry pack. We'll get into that later. Okay, don't worry about the C3 hydration, but after the gypsum is used up and concentrations of the dissolved gypsum decreases, this is what causes the semi-set cement paste to completely lose its plasticity, then that's called final set. So you're going to get an initial set, and then you're going to get final set when you lose that plasticity, and you can walk on it. Okay, we have a cement out there now that we're taking Portland, and we're blending it with limestone dust. Okay, and a lot of the limestone dust that you had in the crushed limestone aggregates or Carsey exceeds the minus 200 criteria. Okay, we need 0 to 1%. You can go up to 1.5% if that additional 0.5% is not clay. And when you have typically 100% crushed limestone, it's rock flour, rock dust, if you want to call it. And we were always getting fairly good strengths at Carsey in the previous labs. Even though our minus 200 was excessive, it was possibly more limestone dust. And they found out now that if you take limestone rock flour, if you want to call it, real fine crushed limestone, mix it with Portland cement, it actually gives you better strength. So now the cement manufacturers are actually manufacturing a Portland limestone cement, PLC. Okay, we're not going to get too much into it, but it emits a lot of the greenhouse gases because you're going to need less cement, Portland cement. The cement manufacturing industry is one of the biggest culprits of emissions and greenhouse gases. That's why the push is always to try and reduce the amount of cements we use. Okay, these are the principal compounds in composition of Portland cement. In the past, you had to know these. I've taken them out for this year. Okay, you have to know the name of the compound and the abbreviations, because these are the principal compounds that are produced. And by varying the amounts of these compounds, we can make the 6 various types of cement. Okay, here are the Portland cements you have to know. Don't worry about the compound composition, but you have to know GU. You'll have to go individuals. Okay, MS, moderate sulfate. MH, moderate heat of hydration. HE, high early strength. LH, low heat of hydration. HS, high sulfate. In Winnipeg, we use HS, anything below grade. Caissons, piles, maybe grade beams that are buried, maybe walls that are buried for an underground parkade. Anything exposed to our clay soils in the Winnipeg area, HS, automatic. No ands, buts, or ifs about it. GU, general purpose, is basically our Portland cements, anything above grade, pavement, slabs, anything above exposure to sulfates. You'll read in the city of Winnipeg where they talk about an early open pavement mix. In other words, they used to always refer to it sometimes as a high early. They don't use high early cement. If you want to get a quicker strength, in other words, you're going to pour a slab downtown Winnipeg on a Friday, and you want to open it Monday to traffic, you're going to use what they call a high early strength concrete mix. And what they do there is they just use general Portland, GU, but they increase the cement content. Okay, so instead of, say, using 340, they may use 380, or they may use 400 kilograms of cement. So in other words, they're making a stronger concrete mix. Not the fact that they need it for loading or capacity of cars. They just need it to get that 20 MPa quicker. They can open pavements in the city of Winnipeg if they get 20 MPa. So in other words, if it typically would take you a week to get 20 MPa, now they can get it in about 3 days. They just boost up the cement content. Low heat of hydration is what you would probably use at the kiosks, the big hydro dams, where you have mass concrete, okay? Because the heat of hydration is what is generated from the hydration process. When cement and water come together in a chemical reaction, it's called hydration. With that, it generates heat. And at one time, there was a myth, and there still is with some contractors, oh, I don't have to heat concrete. It'll never freeze because it creates its own heat. Balderdash. Try and place concrete at -5 without any type of protection and see if it doesn't freeze. It'll freeze. It'll freeze. Yes, there's a heat generation, but not enough to prevent it from freezing. Now, when you got mass concrete, large fixed sections, maybe a big pile cap, maybe having a big housekeeping pad for a huge generator or a huge compressor, where you may be looking at something that's 3 meters by 3 meters by 3 meters. That temperature inside that core of that element, 3 meters by 3 meters by 3 meters, is huge. That's bigger than your room. The ceiling height is only 8 feet. So you can imagine the amount of heat buildup in the inside of that big concrete pedestal or big block, okay? So we've been able to produce various cements for our various environments, okay? So GU, no GU in the name, no the symbol MS, because remember these used to be type 10, type 20, type 30, type 40, type 50, okay? You can see here which principal compound controls the various properties. So in other words, you can see here C3S, C2S. Don't worry about it, you're not going to be quizzed on it, but by those principal compounds all have a bearing on the physical development of that concrete or that cement. Okay. When Portland cement is mixed with the water, the hydration reaction occurs. So that's why as soon as at the batch plant, when the aggregates and cement come together, even before the mixing water is added, there's probably enough water in the aggregates, especially if the moisture contents are high. Hydration is going to start right from that point. Okay, here again is the types of Portland cement. Okay, in the States, type 1 was GU, type 2 is, they called it the moderate sulfate and high sulfates. Sorry, yeah, moderate heat of hydration, and moderate sulfate resistance. They grouped it together. Type 3 was their high early. Type 4 was their low heat of hydration. And type 5 was their high sulfate resistance. But don't worry about the US. We're in Canada here, so these are the ones we're interested in. Okay? I'm not going to go through these in great detail for a simple reason. It gives you an idea. Typically pavements, anything above grade, pavements, floors, reinforced concrete buildings, HS high sulfate, areas that have high sulfate concentrations. Okay? The HS will usually have lower strengths than GU at the earlier age, but at 28 days, shouldn't have a problem. So typically on a GU cement, within 7 days, you should get 70 to 75% of your 28-day design strength. Whereas if you're using HS, high sulfates, typically you might only get 65 to 67%. So it gives you an indication. Don't panic if your HS cements are typically lower than what you're used to with pavement. It's because of the composition. When you work with concrete and you understand the basics, you can understand it. And why do we make 7-day cylinder strengths? Why do we test concrete at 7 days? Anybody? Or at 3 days? A couple of reasons. Sometimes we test concrete at 3 days. Sometimes we test it at 1 day. But typically you'll see specifications where they state 7-day strengths and 28-day strengths. Why 7 days? 28 days is the only one that's accepted. You cannot reject concrete and have it jackhammered out on a 7-day strength. It has to be a 28-day strength. So why do we take 7-day strengths? Anybody? Ron, you concrete gurus?
Just to check it and make sure everything's okay.
Okay, but how's that going to dictate? How do we know that? You're on the right track. Go ahead. To predict the final strength. Exactly. We know that if we're going to get 70 to 73 to 75%, that's the relationship between 7-day and 28 days, we can use it to predict. If we got a 7-day strength at only 50% of the anticipated design say of 35 MPa, we might say, oh, we got some problems here. What happened? Okay. Doesn't mean the 28 days isn't going to make it. Maybe there's something wrong with the 7 days, but it's used to predict, are we going to have any issues at 28 days? Are we going to achieve our 28-day strength? Because we know the correlation between 7 and 28. Now, sometimes we do a 1 day or a 2 day or a 3 day, and that is done to sometimes say, okay, can I put my structure into service? For example, can I open my pavements? I'm going to do a 3-day break. I cast on Friday and I'm going to test it on Monday. Can I put my pavements into service? Can I strip the forms? Okay. You're pouring grade beams, you're pouring walls. Can you strip your forms? Can I start loading some loads onto my structure? Can I start putting some strength bearing elements onto my pile caps? Okay. So a couple of reasons. Stripping forms, putting things into service, and to predict, are my 28 days going to make it? Good. Okay. So again, moderate heat of hydration, low heat of hydration. And these are areas where you have to be careful. It's also if you're involved in construction and you're pouring concrete in winter and you've heated it and you hoarded it. Okay, it's minus 40 outside, but in your hoarding, you're at about 15 degrees Celsius, nice toasty 20 degrees Celsius. That's where you eat your lunch. That's where you strip off your big coveralls and your big Carhartts because it's warm in there. Now, keep in mind, there are specifications. You just don't, after 7 days, or whatever the spec calls for, to heat and hoard, you just don't strip that hoarding off. Boom. Because remember, it's 20 degrees in the inside, and it's minus 40 on the outside. You strip that hoarding, in 1 day, what happens? Anybody? Cracks. From what? Thermal cracking. Not only is your concrete hot on the outside and warm, okay, the inside core, if you had that big element, let's say 3 meters by 3 meters by 3 meters, that temperature on that inside of that concrete, and just moving to the outside surface of the concrete, there's a pretty big temperature gradient. Now you're moving it outside to minus 40. So now the specifications that if a contractor is going to remove the hoarding within 7 days, he has to start reducing that internal temperature slowly, such that there isn't a big thermal shock when he takes off the hoarding and bang, you're at minus 40. And there are CSA standards for that that gives you the amount of temperature drop. So we know that concrete creates heat. We also put heat on it. So we got to be careful. Cold weather concreting is totally different than warm weather or hot weather concrete. And hot weather concreting is different than normal concreting. Okay, so we can go on the cold end, we can go on the hot end, and we have to take things into consideration. Are you casting in the Gobi Desert where it's 35 to 40 degrees Celsius? Or here in Manitoba? Okay, so temperature. Ambient temperature has a big bearing on how a structure and concrete performs. Okay, cements. High early, again, gives you quicker strength gain. Type HE is used for early form removal or when structures need to be put into service quickly. Okay? In our case, we just use more cement because now, look at it from a point of view of the cement producer. He now has to have an extra silo. He's probably got one silo for HS at his plant, one cement silo for GU, and he may have one cement silo for fly ash. Maybe he even has a cement silo for silica fume. If he's going to carry so many different types of cements, and he only uses them the odd time, it's not very cost effective. So if you need an early strength gain, you want a higher strength gain early, just beef up the mix, add more cement to it. Designed for a stronger 28-day strength, your 7-day and earliers are going to be also proportional. Okay. It is good for cold weather concreting. Yeah. It should not be used in large mass structures because the higher amount of heat generated can cause expansion and subsequent cracking of structures. Okay. So this is where you would use LH, low heat of hydration. If you've got lots of it going in, like the hydro projects and that type of thing, where you're going to have large, big concrete masses then obviously your plant is going to be set up for that. And you're going to have an extra silo and you're going to buy it. It's not readily available, but it is produced in the West. So you have to, again, order it, keep on top of it. These are the designations, don't worry about it, but this is where limestone, remember, if we're mixing Portland cements with crushed limestone dust, it's now called GUL. And what that really means is Portland limestone cement. Okay. What are the influences from the different types? Rate of setting, ultimate strength, heat of hydration, and durability. Okay. So these are the factors that are influenced by the different types of cement. Okay. White Portland cement, don't worry about it. That's usually for architectural stuff. Masonry cements, obviously, if you do masonry, you can use the masonry cement for your mortar. And those of you that have maybe been bricklayers or have done some work with bricks, there's usually a type N and a type S mortar. Okay, one is non-bearing, one is bearing applications. Okay, these are the cements that I want you, sorry. The next thing here is there's various tests, that the cement manufacturer has to perform. These are sometimes referred to as mill reports. Okay, the ready-mix producer buys cement from the cement manufacturer, and he's going to ask for the mill reports. The owner, City of Winnipeg, may ask for the mill reports. The contractor is then working with a ready-mix producer and says, I need mill reports from your cement manufacturer. Concrete manufacturer will then contact Lafarge, Wholesome, whoever they're using as their manufacturer of cement and supplier, and say, I need your mill reports for this week of production, for this month of production, or to represent those loads of cement that you delivered to me last week. I need the mill reports from those batches. This is all records that is required, okay? And there are some key tests to be run. Don't worry about the frequency, but these are the tests that I want you to know. Setting time, fineness, compressive strength, expansion or soundness, in other words, change, heat of hydrations, and these are typically just done on MH and LH, moderate heat of hydration and low heat of hydration, and the sulfate resistant. You're going to run that typically on your MS and HS. So these are the 6 key tests that they run. Each one of them has a bearing on how your concrete is going to perform. Okay, the setting time of cement is going to have a direct influence on how quickly your concrete is going to set up, or not quickly set up. And there are ranges that these cements have to meet by CSA. So keep in mind, setting time from 2 different cement manufacturers might meet CSA criteria for GU, but they may be totally different for setting time. One may set up on the lower end of the scale, one may set up on the higher end of the scale. They both meet CSA standards for setting time because it's a range. Use it in a pavement, and a contractor may be used to one type of cement for so long because he's worked with it. He now knows I've got so many hours to play with it. And all of a sudden, he switches cement suppliers. And he doesn't really work with the cement supplier or their cement. Now the setting time might be quicker and he might get caught. And that happened with MI many, many years ago when I worked with them with quality assurance when we were finishing off the East Perimeter Highway. Mulder Construction was doing the work. They used, I think, a different cement supplier instead of Lafarge or whoever it was at the time. I think they went to Hudson Cement out of the States. Setting time, okay, meets CSA standards. But Mulder was never used to working with that cement. And it started getting away on him. Started setting up a lot quicker. This is key to setting up your work. If you're going to work with concrete that sets up quicker, you're going to have the manpower. You're going to have the equipment to be able to place it and finish it. Okay? Keep in mind, setting time is going to be crucial. The fineness is the grinding of the cement. If they grind it too fine, it's going to affect the setting time, and vice versa. Compressive strength. The cement itself has to have a certain strength. And because the cement itself has a certain strength, you're not going to predict that it's going to meet your concrete strength because there's other factors that influence it. Temperature, mix design, sand grading, admixtures, but there has to be a minimum cement strength. And they actually just make cement cubes with silica sand or graded sand. And again, if their cement cubes are not meeting the CSA minimum criteria for that type of cement, they got to look into their manufacturing process. Expansion. Okay, volume change. Is it going to expand? Heat of hydration, again, and sulfate resistance. So it's important that they run melt tests. There's other tests they run, but these are the key, okay? So again, you don't have to know the frequency, like one test for every 1,000 tones, but know the 6 tests that they run. Setting time, fineness, compressor strength, expansion or soundness, heat of hydration, and sulfate resistance. Any questions so far? Okay, setting time, initial set, that just gives it the definitions. I want to go through quicker because we've still got the other units to cover. Fineness, the finer the cement particles, the higher the surface area exposed to water, which speeds up the release of heat and the hydration, resulting in higher early strengths, also sets up quicker. So again, if he's grinding too fine, it's going to be a problem. If they don't grind fine enough, you're going to have a problem. Compressive strengths, soundness, heat of hydration. Okay? Any questions to that? I went through it quicker because we want to cover a fair amount here. Okay?
Hey, I have a question.
Yeah, go ahead.
So how exactly do they how do they regulate the heat when they're pouring concrete in cold weather? Do they set up like little shelters over where they're pouring, or how does that work?
Remember I talked to you about heat and hoarding? A hoarding is you enclose your element. If you're pouring, say, a big housekeeping pad, let's say it's 2 meters by 1.5 meters high and 3 meters, they just close it in. They'll build hoarding. They'll put some Herman Nelson air ducts into it. Remember, never use fossil burning fuels inside. Carbon monoxide is going to react with the calcium hydroxide of your cement and it's going to peel your surface right off. So you set your heaters outside and you just run heat ducts, just a hot air into it. So you're going to heat inside. So if it's minus 25 in winter, you're going to set the heat inside to say 10 degrees or 15 degrees. I like to keep the temperature of the hoarding on the lower end. You don't need 22 degrees Celsius. You can pour concrete at 4 degrees. That's actually the best temperature to pour concrete is about 4 or 5 degrees Celsius. And yet you reach specifications where they say the contractor shall heat and hoard at 5 degrees C. Yeah, but anyways, so keep it at 10. You don't have to cool down as much after if you're going to rip your hoarding down. So you want to keep that temperature. In other words, you're making ambient temperature to resemble summer operations, if you want to call it that. Okay, in the Arctic, they put up these big golf domes like you see on Kenaston there, the golf dome. They'll put those up and they actually build structures within them. Okay? Huge, massive golf dome type of structures, and they build inside. They'll have machinery running in it. They'll be placing granular base so it doesn't freeze it. They compact it, and then they'll start erecting their concrete. You just heat and hoard. And then when you're done, you dismantle it. Hopefully, concrete has set up. You don't have thermal cracking and so forth. Okay, it's called heat and hoard. Actually, I don't know why they call it heat and hoard. Usually you hoard in heat. You got to hoard it first before you can heat it. But anyways, we'll see that in the specifications in numerous construction sites. Okay, that answer it?
And then if you're pouring in a really hot environment, you just kind of do the opposite, right?
Well, in hot environments, a lot of times in a center port, we had to throw ice as part of our mixing water into the concrete because we had a stipulation where we could not have concrete any hotter than 20 degrees Celsius. Well, if your mixing water isn't cold enough at the batch plant and then your ambient temperatures are 33, 35 degrees Celsius outside, your concrete is not going to cool down. So we substituted a certain amount of mixing water by using ice, which eventually melts in the concrete, and then you got cold water. So that was one way. But you can put up sunscreens, sunshades. Also, there is a nomograph that tells you whether you should be even pouring concrete when it's, say, 30 outside. Because then you got to take into consideration your concrete temperature, your relative humidity, your wind speed, okay, and the ambient temperature. And then there's a graph that you follow through, and it'll tell you your evaporation rate. And I don't know it from memory, but a certain evaporation rate of water from your concrete is going to cause cracking. And I remember years ago when I was with MI, Nelson River was on Highway 75. Young engineer came out. He was with Nelson River, and he himself said, "No, guys, we're not pouring concrete." He told MI, he says, "Yeah, you got a beautiful day to pour concrete, but it was like 33, 35 in the summer, and we were paving Highway 75 from Morris, I think, to St. Jean, if I'm not mistaken, but whatever." He just says, "No, I'm going to have cracking of my pavement, too much moisture loss from my surface." It's costly to put up a sunscreen. It's costly to try and put up a wind barrier because the wind speed will many times dry that surface right out. Okay, so summer hot weather concreting is just as difficult as in winter. And I talked with one contractor, and he says, "I prefer to pour in winter all the time." He says, "I can control my winter temperatures. I can't control my summer temperatures. If it's too cold, I'll heat and hoard." And he builds that into his price, okay? If you're going to be bidding a job and you know you're going to be doing concrete in winter, you have to allow for that. You know, your cost of heating, cost of erection, cost of materials to erect those hoardings, labor, material costs, so forth. So summertime is not as easy as it seems also, you know. That's why if you're pouring concrete 10 degrees, 15 degrees, that's ideal. That's beautiful weather to pour concrete. Okay. Any other questions? Night pouring with ice water. Yep. Okay, night pouring is not a bad. I love night pouring, but a lot of the people have to get their beauty sleep, and they don't like the noise in a residential area. So they complain to the city. They complain to the counselor. "Well, I can't sleep because I got to get up at 6 o'clock in the morning." Suck it up. Night pouring would be ideal. Not only it would increase the rate of production, we'd have a lot of less closures, length of time of closures. I mean, that is even the whole gizmo now. People are talking about, why are we only working on during the day and maybe the odd weekend when we're doing reconstruction of our Winnipeg streets? A lot of the public complain, why aren't we going 24 hours a day? Why aren't we going 24 hours a day? Okay. Easier said than done because it takes all kinds of parties. Maybe you don't have to do some work during the day, you can do it at night. But to pour concrete at night, now you got to have your consultants out there, they got to have double the staff. You got to have a ready mix producer that is willing to batch at night. If it's a big job, you got to have the cement haulers. Mind you, they haul 24 hours a day anyways from Alberta to bring cement into the plant. Because many times on a big job, they're filling up that silo 2-3 times a day. Okay, so one tanker comes in, a few hours later, another tanker comes in, a few hours later, another tanker comes in and loads up his silos. So night pouring, there's so many other circumstances that come into play instead of just, "Oh yeah, I can pour concrete at night." Yeah, you can. What about all the other factors that come into play? Okay, but it can be done. It can be done. You just have to gear up for it. And we have to quit saying, "I can't have any noise after 8 o'clock at night," or, you know, and hey, it is a disturbance. It is a disturbance. We drove piles at Centerport during the night, and one irate resident came in and tried to rip a strip off our superintendent. Well, next thing you knew, we had a screaming match between the superintendent and the irate residential homeowner in the field office because he couldn't sleep at night. What do you do? And we had authorization to drive piles at night from MI because we had to get the piles driven for the bridge structures. Okay. Any other comments? I'm kind of getting off topic, but this is what I miss by not having these face-to-face classroom lectures because we can get into a lot of good discussions. Okay. Any other comments on cement? Okay. I had to go through quickly. I'm sorry on that, but anyways. We'll switch to mixing water, which is very, very brief, so we'll get that out of the way. Now I can, we can go longer with this. I've allowed 2 hours and 15 minutes. I don't know what you guys are on. If you want to go longer with these lectures, I don't have a problem with it. However, you guys already have different commitments and different schedules, so I realize that. Okay, so let's switch to mixing water here. I'm going to unit 5. Okay, any comments? Okay, this is fairly straightforward. What water do you use for mixing? If you can drink it and you don't die from it, it's good for concrete. So in other words, potable water, the water that comes right out of your tap, that's ideal. You know it's going to be okay because it's been tested, and all the ingredients that have been determined from a chemical analysis of the water is not detrimental to concrete, as long as those levels are within a certain range. But typically, potable water is the ideal water for mixing concrete. It's the key ingredient in concrete. Okay, without it, you can't have concrete. So you got to have water to kick over the cement in a chemical reaction. The water and cement react, which causes the hardening of concrete, hydration. Okay. The water needs to be pure to prevent side reactions from occurring, which may weaken the concrete or interfere with the hydration process. Okay, this is key. We know potable drinking water works. Okay, we know that. Now, if you're going to be working with concrete in a remote environment, say up north somewhere, and you're going to be using water out of a lake, water out of a stream, whatever, what's in it? There could be ingredients in that water. It may not jeopardize your strength. Let's say it doesn't affect your strength, but it could affect durability, could affect finishing, could affect staining, could have adverse effects other than strength. Okay, so this is where a well-planned project comes into play. If you guys are going to be working as contract coordinators and you're going to be batching or building a water treatment plant in a remote settlement, and the contractor says, I'm going to draw water from this lake, okay, I'm going to have pumps set up in the lake, and I'll put it into my water tank, and from the water tank I can pump out X amount of water for the concrete I'm going to be mixing. You know that ahead of time. Get that water sampled, because you're not going to get water results overnight. It's a little too late when he's ready to batch concrete and you haven't even tested your water. So again, it's like anything else. What is the source of his raw materials? And in this case, the water. Get it tested. You never know what's in it. Maybe there's high algae in it. pH could be different. Research and field works on concrete indicate a water cement ratio of about 0.25 to 0.3. That's all you really need for strength. So then why are we adding so much more water? Anybody? Why are we going 0.45, 0.5, 0.6 water cement ratios? Why don't we just design everything at 0.25, 0.3? Absorption, but really what other reason? Not so much absorption, because you're going to take that into account whether you're designing for 0.2 or 0.3. Evaporation from the mix, yeah, okay. Workability, right. The rest is workability. If you can't work it, what good is it? If you can't place a pavement down and finish it off, you can't build an ice arena, ice surface, you can't finish your floor slab in your basement or in for a big warehouse, what good is it? Workability. You got to be able to put water in, make it workable, but at the same time, not jeopardize the strength development. And that's where you design and do trial batches. But as far as the actual hydration to take place, 0.2, 0.3 is all you really need. The rest is for workability. So that's a really good reason why. What two reasons does water play in concrete? Hint, okay? And here again, you can see, this is just a relationship between the water cement ratio and 28-day strength. Okay, you can see air entrained concrete and non-air entrained concrete. And right off the bat, you can see that at a certain water cement ratio, non-air entrained concrete gives you better strength. But depending on for the inside floor slab, okay, you don't need it for freeze thaw durability because there is none. But maybe you can't finish it as well. So even a lot of designers will use air and train concrete for inside because of finishability. It's easier to finish air and train concrete than non-air and train concrete. But here's the development. You can just see that as the water cement ratio increases, compressive strength decreases. So that's why we always use a lower water cementitious material ratio for strength development. The lower the water cement ratio, the higher your strength, okay? So here looks like a pretty good graph to figure out some relationships, okay? Like I gave you on the quiz. Learn how to read graphs. They're very important. That's why we graph them, okay? Water quality. Almost any municipal water or any natural water that is drinkable with no pronounced taste or odor is satisfactory for mixing water. And there's certain criteria. When you test that water from a northern remote site, you're going to actually use the cement that you're going to be using, and you're going to make cubes with this water, and you're going to make cubes with standard water, standard control water, let's say water from your faucet. And the strength has to be a certain ratio between the water that's in question versus the standard cubes, okay? And that's one way that they're determining, yes, from strength, well, that water will give us the strength. It might give you 95%. I can't remember what the limits are, but the cubes have to be a certain percent of the strength from control cubes, okay? Excessive impurities affect not only concrete, oh, hold on a minute, my screen for some reason, but may also cause efflorescence, staining, volume instability, corrosion of reinforcing steel, and reduced durability, okay? So now we can see why water is important. It may have adverse effect with some of the other ingredients, especially reinforcing steel. It may not react very well with air entrainment, who knows, okay? When in doubt, get it tested. Although some impurities can have little effect on the strength and setting time, durability and other properties can be adversely affected. You don't know. Why take the chance? If you don't test the water and you start using it for batching concrete, okay, you may have strength problems, you may not, but you may have efflorescence, which is the staining or the leaching of the gypsum salts that you see sometimes. You may even see that in your laundry room sometimes when the water around your drain, concrete around the drain, okay, water from your sump pit, they'll get a white staining effect, almost like a little powder. And that's the efflorescence coming out of the cements. So you gotta be careful. Seawater, algae, and wash water, sometimes they're used, okay? So that's it for water. Know the importance of water and why we use it. Obviously, if you don't have water, you can't make concrete. And it will have an effect. It may affect setting time. It may have other adverse effects. Water for the hydration and for workability. Any questions on water? Okay. But again, this is like anything else. When you're working as a contract coordinator, keep in mind that you have to look ahead. Some things that are requested, it's like even something as simple as doing density testing. Many times the contractor fails to submit the sample for a standard Proctor test, okay? He doesn't do a standard Proctor test. So he calls for densities and he says, okay, give me % Proctor. Wow, where's your Proctor value? You never submitted it in. You know, I've been at this for 48 years or so, and to this day, contractors still sometimes forget, same contractors that I've dealt with, different people, mind you. Well, I didn't send in a Proctor value. They don't understand the relationship between field densities and standard Proctor and whether you need 95% compaction or 98% compaction. Okay, so this is where is the difference between a good contract coordinator and one that isn't. Okay, any questions on water? Okay, we've got admixtures and fly ash. Do you guys want to continue or do you want a little bit of a break? And we'll pick up on this? Or do you want to switch to the lab and you guys can read up on fly ash and admixtures? Break, yes please, break. Okay, let's take a break. Now, should we go right into the lab, or do you want to continue for, say, even another hour and a half after the break, and maybe we can finish off the lectures and then get into the lab? The lab won't be too much because it's more taking your mix design that you guys are working with now and converting it to a 0.1 cubic meter batch. So after the break, should we finish off the lecturing? Lab. Okay, keep in mind, add mixtures, there's a fair amount, but again, I've highlighted key areas. Okay. Yeah, I mean, I can read, you guys can read just as well as I can read. So again, if you have any questions, call it the theory part, the lecturing part, get in touch with me. Okay, I've highlighted the key issues, but again, well, the notes usually are highlighted already, okay, in your learn. But for water quality, these are already highlighted. I've highlighted them ahead. Now, sometimes I highlight an additional one. Well, just highlight it as I'm lecturing, okay? But the ones right now on Learn should have the highlights in it. All the ones I have downloaded, there have been no highlights. Maybe you downloaded too early. Yeah, the comments are the most valuable part. And again, they'll come with recordings. So the next two units, Unit 4, fly ash, and the admixtures, I won't be able to comment on them. Okay. You download it right now and there's no highlights whatsoever? Conrad? Hello, Conrad. You said that, yeah, none whatsoever. Okay, I'll have a look at it because I thought I had highlighted. When did you download them? Or it might be a Learn thing. Yeah, I noticed that with Learn sometimes too, but let me check into it. Okay, let's have a break. We'll come back here in 15 minutes. So say, let's come back here at 10:25. In the meantime, I'll look to see on Learn. They are highlighted, Sean is saying. So, yeah, check your Learn though. Some are, yeah, they are highlighted. Okay, thanks, Sean. I thought I did, but then again, my memory. Okay, I've got a good memory, guys. Really good. I don't think this is short. Okay, let's come back here at 10:25. I'm just going to stop the recording, but I won't shut down the WebEx. Just continue from here on. Okay. Yeah, we'll try to download. Okay, Conrad, try the download button. Okay, let's just stop the recording here for a minute and have a break. We'll come back here at 10:25. Okay, we're back. Okay, anybody got their cup of coffee or their toast or whatever? Okay. Okay, we're going to look into the lab. Now you're finishing off your lab 3, which is doing mix design for, excuse me, for the aggregates that you supposedly tested, but we had the fictitious data. So remember, you're going to be using the specific gravity and the absorption data from your previous labs for your mix design, okay? Remember that it's based on dry basis, not SSD. When mix designs usually are submitted from the industry, they are usually proportioned on an SSD basis. That just means that it won't take on any water and there's no free water. But when you're designing on a dry basis and taking into account the water is being absorbed and the mixing water, minus the free water. So in other words, it's designed on a dry basis, but sometimes you can present the mix design values on an SSD basis, okay? We're doing dry basis, okay? Okay, let's go into the lab. And this lab is what you've essentially been doing. You would go to Carsey, and this would be filled out ahead of time because you're going to be batching. In Carsey, we actually batch 0.07 cubic meters. We find that anything larger than that just doesn't fit into the mixer very well or into the wheelbarrows. So in other words, you actually weigh out the 0.07 cubic meters. We're going to design for 0.1 meter. Just that much easier because this is just a fictitious virtual lab. So now you're going to actually determine what are my batch weights for 0.1 of a cubic meter. So I'm going to put up a couple of share content here and we'll have a look at it. There's a form that we use when we fill out, okay? I have a blank form and I also have one that's an example from previous labs. So it is just an example. And this is what you would have been doing had you physically been batching the concrete. So you're still going to fill it out. And then we're going to keep it for the week after when you're going to actually do the calculations for compressive strength and flexural strength. And I'll get into that a little bit more. So let's look at the share content here. Okay. So this is a form that we use that if you're doing your calculations for a trial batch. In other words, you go to Carsey, you weigh out the aggregates, you weigh out the water, you measure out your air and training agent, you weigh out your cement, you weigh out your fly ash, and you batch it. You've already got the masses for 1 cubic meter, okay? So here you can see the concrete batch size. Okay, so if we looked at the example, and I'll switch that right away here. But the concrete batch size here, we're going to look at 0.1 cubic meters. So really, your coarse aggregate mass for 1 cubic meter multiplied by 0.1 is going to give you your initial mass there. Fine aggregate, whatever you worked out, dry bases per cubic meter times 0.1 goes in there. Same with the water. Same with the fly ash. Same with the cement. Pretty straightforward. Okay? Now, I'm going to pull up the example because it might be easier to read and understand it. So this is what we essentially do if we're doing a trial batch. And again, this is was kind of formatted in a textbook. I think you may have even seen it in parts of Chapter 9, what I've uploaded for you. Okay? Different organizations may use it a little differently. And with it then, we'll have another page when we're actually physically testing the concrete. So let me just call up the other one here, and we'll go for the example. Okay? I'll reduce that a bit. Everybody see that okay? Okay, here it is. We're batching 0.1 cubic meter. So we actually says that 1 cubic meter for this example, 53.5 kgs of cement. Okay? Now, you go through the calculations. This example doesn't have fly ash, okay? Because back then we weren't using fly ash. So, but it makes no difference really as to the calculations. It's just one less ingredient. So we figured out that for 0.1 of a cubic meter, you need 53.5 kgs of cement, 21.2 of water, 49.5, 91.9. And for their example, and we'll look into this a little bit more, they decided that 60 milliliters of air, which was the air and training agent that we used, gave them the air that they needed. Okay, they also designed for 7% air. Anyhow, so in other words, you would go to Carsey, you'd weigh them up in 5-gallon pails or whatever, and then you would dump them into the mixer and you would mix it. Now, for batching concrete, there's a CSA criteria for trial batches, making trial batches in the laboratory. 823.2-2C, I believe, and that's, again, you can download that through the Red River College CSA link, and you'll be able to pull up that CSA standard, okay? Now, so you weigh these out, and then you dump them into the mixer. But when you dump things in the mixer, don't ever dump all your water. This 21.2 kgs of water is also to account for how much is going to be absorbed, okay? So you would use your adjusted water added to your total. Okay, so this is your total water. Now this column here says final mass. Well, if you're going to use all your aggregates and all your water, these would all be zero. But I just said that you don't add all your water because maybe your slump is going to be too high. So as you're batching concrete and you've held back some of the water, you look at your mix. Is my slump good? Is my slump going to be good? Is my slump going to be wet? Is it going to be stiff? In this example, this group did not need all their mixing water. Okay? They eyeballed the slump in the mixer. I mean, typically you can drop some concrete out of your mixer and do a slump test. But again, you're taken away from the mixing time criteria. Keep in mind that trial batches also have to follow a CSA sequence. It's a test like any other test. So anyways, they decided that we don't need all our mixing water. So how much did they add? Well, they just go back and they weighed. But they didn't throw in. They had 1.8 kgs left over. So actually what they used here is 19.4. And you can see here that the mass used is obviously column 2 minus column 3. So 53 minus 0 is 53 and so forth. So here they actually used a little bit less water. Okay? And if you total all this, T stands for batches, your total here per batch ended up being 214.3 kgs. So their batch of concrete is 214.3 kgs. Oops, sorry. Now, obviously there might have been a little bit of mass of the 60 milliliters, but it's so minor, you wouldn't account for it. It's a volume thing here. So it doesn't come into play for mass. It's just a certain amount. And we would actually just have that in a small graduated cylinder in cars. 60 milliliters isn't a lot. Okay? So now, you batch your concrete. Now you got to do some tests on it. Okay? And we're going to make cylinders. You're going to make flexural beams, specimens. But they did a slump test. And some of you may or may not really know what a slump test is. And we're going to cover that more when we get into the production of concrete and transport of concrete. But slump, does anybody know what slump indicates? From a test point of view, what does a slump indicate? When you do a slump test. Workability? And who mentioned workability? What is it? I want to get on my chats here. Okay, I see consistency, I see strength, consistency, 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 strength, viscosity, consistency, workability. Those that have stated consistency, you're correct. Not workability. Now, that's an argument. A lot of people say, no, it is workability. No, it's not. If you did a slump on concrete mix A, and you did a slump on concrete mix B, and they were both the same slump, but one you can finish, one finishes really well, and one is impossible to finish, how could that be workability? They're both the same slump. If you're using the same mix, it's an indication maybe of workability because the slump on the same mix. But the slump test is a test for consistency. That's why you are determining one batch versus the other batch. You got mix design A. Load 1 comes in, has a 75 milliliter slump. Load 2 comes in, has 75 milliliter slump. Load 3 and load 4 and load 5 and load 6, they all have 75 millimeter slump. That's consistent. That tells you that batching is consistent. The ingredients, the mix design has to be consistent. But if you come in with mix design A and one load is 70 and one is 110 and one is 50 and the other one is 140, another one is 90 and another one is 75, what's happening? Why is it all over the map? That's non-consistent. So workability is not dictated or determined by slump and not water cement ratio, because there's a lot of factors that affects the slump other than water. Yes, water may be one of the biggest culprits of changing slump, but the sand grading can change. The ratio between sand and coarse can change. Admixtures can change. A job arrives at a job site and all of a sudden you see a slump of 140. Should you panic without knowing anything about it? Anybody? Maybe it's a super P-mix, super plasticizer, which are high range water reducers. Yes, you're right, Sean. Don't panic. First of all, find out. If it's been designed for a slump of 90 and it's not and it doesn't have high range water reducers or super plasticizers added to it, then yes, there's something to panic about, because it's designed for 90, you've got 140. Now maybe they added a super plasticizer on site. Slump goes up. That slump is a chemical slump. It's not a water slump. It's for workability, okay, or placement. So again, water is not the only factor that can change a slump. So it doesn't give you any indication of water cement ratio. In fact, some people are thinking that the slump test is useless. Why even have it? Okay, so we'll get more into slump later on and how we design. Now, when we're designing for a slump, yeah, we're using slump as a criteria to determine how much water we need. But after that, you don't know what's causing the slump to change. Okay, so anyhow, it's a slump. So here in their mixed design, their proportions that they came up here with, they did a slump test. Okay, they emptied the mixer, they dumped it into the wheelbarrow, and they're sampling the concrete from a wheelbarrow. Those of you that have done concrete testing in the field through some of the testing agencies, you're all familiar with the slump. Here it's recorded to the nearest 5 millimeter, 90 millimeters. They wrote 92. You can't read 92. It's impossible. So I wrote in here, report to the nearest 5 millimeters. Slump is always recorded to the nearest 5. They did an air content. Now, it was 7%, and they wrote 7, but you got to report it to the nearest 0.1. If you don't write 0.0, I don't know that you know that it's to the nearest 0.1. For all I know, you might think it's to the nearest 0.2. So you got to put 7.0. Okay? This is to the nearest 0.1%. If it's 7.1, then it's 7.1. If it's 7.5, it's 7.5. Concrete temperature. Again, it's recorded to the nearest 0.5. Now, there are the 7 tests that you would typically do if you're going for your ACI concrete testing certification: slump, air, density, temperature, casting cylinders, and air content. Okay. Now, for temperature, you record to the nearest 0.5 of a degree C. So again, 16.0 or 6. If your temperature was 16.3, you would record 16.5, okay, to the nearest 0.5. And on your quizzes, your densities for problem 5, not problem 5, the last calculation on your last quiz, where you had to calculate densities and specific gravity, actually the second last problem, your density and your bucket factor. If you recorded density to 0.1 or to 2 decimal places, I deducted half a mark. Density is nearest whole number, okay? So when you're writing these on a concrete form, you're doing quality control testing, follow the standards. Then here you did a physical appearance. You know, you're working with the concrete. Does it look good? Does it look rocky? Maybe they had too much coarse aggregate, or did it look too sandy? So this is just kind of what you would assess by physically looking at it. When you handled it, when you did a slump test, when you're handling it for your air test, when you're handling it to make cylinders, when you're handling it to make flexural beam specimens. What was the workability like? Good, fair, poor? Okay. So here they said it was fair. With part of the test, you want to do density testing. Okay. Before you make your cylinders, before you make your beam specimens, you did a slump test, you did a temperature test, and you did a concrete test. Now you're going to do a density test. So here it is, massive concrete in container. You fill your air meter pot. We use the same pot that we use for density of aggregate. We're using it for concrete, 7 liters. Okay, you rod it, 3 layers, rod it 25 times each layer, and there's a whole test procedure for it. You weigh it. You weighed the mass of your container prior to filling it. It was 3.85. So now the mass of concrete in your 7-liter pot turned out to be 18 kgs. There was a factor written on the side of the pot. Okay, remember the bucket factor? 141.8 per cubic meter. From that, you can determine the volume of that air meter pot, 0.075. Now you can determine the density of concrete, which is just the mass of concrete divided by the volume of concrete, 2295 kilograms per cubic meter. Okay, straightforward. Now here's a clincher. Remember I said you want to design for 1 cubic meter, but from a ready-mix producer's point of view, you want to make sure you don't shortchange your customers. So typically, when I'm designing, I'm going to design a little bit more than 1 cubic meter. And this is why. If you look at the volume of concrete produced, it's called yield. Okay, what volume does these proportions yield? Did it yield 1 cubic meter of concrete? Well, we can base that from the density test. That's why density test on concrete is very important. Okay. If you look at the total weight of material per batch, 214.3, right? That's how much this all totaled. And you determine that your density, physically you weighed it, okay, in the air meter pot. You knew the volume of your pot. You determined that your density was 2,295 kilograms per cubic meter. If you take your mass divided by your density, you get volume or yield, right? And here, what can you see? 0.09337, it's not too far, but anyway, say 0.093. So what happened? They said they batched 0.01. No, they didn't. They batched 0.09 cubic meters, not 0.1. So these batch weights were designed exactly on 1 cubic meter. But throughout the batching operation, weighing, so forth, there's going to be error. They actually shortchange the customer here. Okay, it's less than design batch of 0.1 meter. So if this was 0.15 or 0.12 or 0.2, or 0.2, you're almost doubling, it would be way too much. But let's say this worked up to 0.15, then okay, you've got a cushion. You're not going to shortchange the contractor. He's not going to get mad at you. Okay, so there's a check also. Now, this is a batch. Each batch is 214.3 kilograms. So they say, how many batches, how many batches totaling 214.3 kgs was there in a cubic meter of concrete? Well, that's pretty straightforward. You got 1 cubic meter of concrete, okay? And you divide it by the volume, and you got 10.7 batches. So if you're saying there's 10.7 batches, should be a check, 10.7, is going to give you 22.95. Okay, that's just a check for a cubic meter of concrete. So these are the tests that you would run, and then you would start making your cylinders, and you're going to start making your beam specimens. But these are the tests that you're going to run ahead of time. And these are the tests you typically would run when you're doing concrete testing in the field. Okay, PCL calls you out. They want a concrete test done on their pour that they're placing concrete. You go out there and you sample the concrete in accordance with CSA standards. You bring it over to where you're going to make your cylinders and your testing, where you're going to leave your cylinders for the first 24 hours, and away you go. So you take a temperature on it, you do a slump, you do an air, you do a density, then you're going to cast some cylinders. And if it's PCL, obviously they're not into pavements. But let's say you were working for Transport Canada and they wanted flexural beams on their runways or aprons. So you would also cast flexural beam specimens. So there's standard 8C, 823.2-8C is the procedure for casting flexural beams, and 9C is for compressive strength of concrete. Okay, there's a lot of information in it. And now you have to understand what the labs have to go through to be certified. Anyhow, so now let's just go back. Let's say we've made our cylinders, let's say we made our beams, but we want to go back here and we want to check everything. So this is the mass that we used. Now let's convert this mass back to a cubic meter basis. Mass per cubic meter. Okay? So if you take C times column 4. Okay? These are the actual ingredients that you use then for cubic meter basis. Okay? If you total these, they get 2293. That's really close to 2295. This is a good check. These are way out, there's something wrong. Okay. 2 kgs on a cubic meter is nothing. So in other words, they were able to confirm their density and their batch weights. So now your cement factor. Why did the cement factor here go up? Cement factor is the actual amount of cement you use. Okay, so for 1 cubic meter, 572.45 kgs of cement. Okay, because they use 53.5 for 0.1. Go through the calculations, 572.45. Why do they get 572.9? Why are they using more cement? Not much more, but they are. Why? Anybody? Tells you right there. Because you're not dividing by 0.1, you're dividing by 0.9. So they're actually using more cement than required. But if the opposite was true, if you actually had 0.15 or 0.12, and you still have the same cement here, you're shortchanging. Okay, we need 541 kgs per cubic meter of cement for our mix design. Okay, if it worked out that we ended up having 540 or 539, which is minimal. However, the client might say, hey, you're shortchanging me. The spec says, your mix design says, a minimum of 541. You only gave me 540. I want a credit on the mix or whatever. See what I'm getting at? That's why yield is important. So if you're going to design for a little bit more than 1 cubic meters, you might go 1.03. Make sure that that cement is based on 1.03. Okay, so here, that's why the cement factor. And that's what is referred to, cement factor, or cementitious factor. Cementitious would take into account having the fly ash as part of your cementing material, okay? Like I said, this example just doesn't have fly ash in it. So here you can see then that they're not shortchanging them on the cement, but the opposite could hold true. So they go through and they figure out their water content. Okay? And here they're just doing a check of percent fine aggregate versus coarse aggregate. Okay? So I was pretty lenient on this. I gave them 10 out of 10 for this data. Okay? So this is actually what I want you to do now. Your mix design that you're going to submit today, Lab 3, go back and do it here. Okay. Now what I'm going to do for the lab after that, for next week's lab, I'm going to give you some data. I'm going to give you a mass of container in concrete, and I'll give you mass of the container. Obviously, I'll give you either the volume or I'll give you the factor. Actually, no, I won't. I'll give you this, and I believe I already gave you these for the density of the concrete aggregate. So in other words, you're going to use the same bucket. I've got all that data information, so I should be able to give that to you. So for next week, we're going to be actually calculating these, and then we're also going to witness through the video a compressive strength test and a flexural strength test. And I will then also give you some data. In other words, I will give you some data on a cylinder. When you're testing a concrete cylinder, what do you have to know to get the strength? Okay. You take a cylinder specimen, it's circular, it's round. You're going to slide it into a compression machine, and you're going to load it. Now, when it fails, you record the load, which I can give you. But what else do you need to be able to determine stress? Okay, because the compression machine only measures load. How do you calculate stress on the cylinder? Cross-sectional area, exactly. So in other words, had you physically been in the lab, you would have been measuring the diameter of the cylinder that Art and I would have been testing in the compression machine. And then based on those dimensions that you physically measure, you then determine. So in other words, don't worry about this yet, because this is what you would have been doing. Here you see that they had to give diameters. Now, our sheet that I've uploaded is a lot better. But anyways, they measured the diameter of the cylinder. They were testing 2 cylinders, okay? One at 7, they were testing one here at 70, but they took 2 dimensions, perpendicular to one another, okay? You measure the diameter of the cylinder at 90 degrees to another, 2 spots, and then you would average it. You get the load off the compression machine, okay, in kilonewtons. Compressive strength or stress is load divided by the cross-sectional area. So if you know the diameter, you can determine the cross-sectional area. And that gives you your strength here. And again, you record to only 0.1, 1 decimal place, not 2. Okay. Come on. But anyways, we'll come back to this a little later here. Let me just, come on, I'm freezing up here. Give me a minute here. So I want to go back to the blank form because I've remodeled this form since then a little bit. Okay, so it's going to be easier to read. Okay, I'm going to go back to the blank form here. And again, this is going to be next week. So for this lab, okay, I'm going to want you guys to calculate this and this. So I will get back to you. I have to get back to you with this mass here. Okay, because everything else you should have. And as far as your slump, air content, and temperature, I'm going to leave that up to you. Put something in that's realistic. Don't copy exactly the same. You know, you're designing for 7%, but it just so happened that theirs worked up to 7%. Some other labs had 6.5. Okay, it all depends again on how much air training agent you use here. You may want to use the middle. Your Derivair air and training technical data sheet is uploaded and learn also. Read the technical data sheet. See what the manufacturer recommends as a dosage rate. You may want to go right down the middle. You may say, I'm going to go a little on the higher side of the average. I may go a little bit below the average. Okay, I want to see what you guys come up with here. Okay, it's not important now. It's just because we're generating data. But this is the data you would physically determine. And I've had people use 60, and their air content was quite a bit lower. Maybe it didn't mix properly. Maybe the amount of water they used was different. Maybe the proportion between coarse and fine aggregate was different. They all had different mixes. Okay, keep that in mind. So let's just go back to this blank sheet, and here it is. If you scroll down to the next page, I had modified it. As time went on, we decided to test more concrete. So here, we tested 2 cylinders at 7-day and 3 at 28. So when you were batching concrete, you made a set of 5 cylinders. And you made 3 cylinders for 28. So 2 were tested at 7-day, 3 of the cylinders were tested at 28. The date cast is all the same because you made them all at the same time. Okay, and then here I just cleaned it up a little bit, so now you got room to record your diameter. So for cylinder number 1, you might say that that's going to be 1A1, 1A2, 1A3. If you're group 1A, you might call that 2A1, 2A2, 2A3, 2A4, 2A5. You would physically write that on the cylinder because you're storing it. So 28 days later, you want to come back and make sure you grab the right cylinders. So you have to catalog your cylinders. So here's the cylinder ID, whatever you call it, the 1A, 2A, whatever. The date tested, well, if you made it today on the 9th, okay, you would have been testing the 7-day on the 16th. And if you made it on the 9th, you'd be testing 7, 14, 21, 28 would be April 9th, give or take. So in other words, 28 days later than date cast. The average cylinder diameter, okay, you're going to have diameter 1, 90 degrees to it, you're going to have diameter 2, your average diameter, the cylinder area. So I just cleaned this up a little bit, okay? So next week's lab, you're going to be given some diameter data and a load. That's basically all you're going to need. From that, you should be able to calculate it. We'll get more into detail on this next week. Same with the beam now. Now, calculating a flexural beam is totally different than a cylinder because now you got span length. So look at those videos that I've uploaded for the flexural strength and the compressive strength. They're by CT or CPPT. They're pretty good videos. One thing to keep in mind, guys, when you're watching these videos, a lot of them are imperial. A lot of them are based on ASTM. I went through them. CSA and ASTM for these tests, I believe, are the same. I got to just double check that again. But look at the mechanics. Follow the CSA procedures. Okay, you've got access now to the CSA procedures because you can go through the library link. When you test a concrete cylinder, you just don't put it in the machine and bang, load it. The rate that you load that cylinder is very important. If the machine loads it too fast, you're going to get a higher break. You're going to get a higher stress. If you load it too slow, okay, your strength is going to be very, very low. So the rate of loading is very important. Same with the flexural beam. Flexural beam now, if you go through it, and we'll go through it more next week, you're going to measure the dimensions, the width and the breadth, okay? Cross-sectional area. Because when you cast a beam, you're going to test it on the side because these are formed surfaces. It's got to be smooth. Because when you make a beam, okay, you got 3 sides, the top is open, you finish it off. But it's going to be rough because you're going to use a float. The other 3 sides are cast against the metal form, a steel form, okay? Now we got to look at length, or the span length. We got to look at the width. We got to look at the depth, okay? Because now we're testing modulus of rupture, flexural strength. We'll get more into that next week, okay? So for the lab next week, I want you guys to fill this out and go through the calculations, okay? Pretty straightforward. And I will have to get you this mass of concrete quickly, okay? Any questions on this so far? Okay, sorry, Fabian, you had a question here. How do we know how much water is going to be used? In your circumstances here, use all your water. For the most part, when we're actually batching this concrete, for the most part, there was only one lab that I can recall, or maybe two labs, had a little bit of water left over. Most of the people will use all their ingredients as weighed out, including the water. Okay. We also have, you got to remember that these absorptions of the aggregates have been determined in previous labs by the students. The aggregates may be somewhat, they shouldn't be different because they come from the same bin, but there's also the degree of accuracy on those absorption rates. You may determine an absorption of 2.0, okay? Maybe it's 2.2. So it absorbed more water than what you're allowed for, okay? So these absorptions, again, are based on tests. And a test is only as accurate as the people that are doing it and the standards that you're following. And then there's just the anomalies of the test itself, just the accuracy, the degree of accuracy. So for the most part, most students use all the water. So for your analysis, use all your water. Okay, so if your water works out here to whatever it works out to, 55 grams, whatever, use it all. Okay, you can base it on that. Is that okay, Pavel? Yes, the adjustment. Oh, you have to use the adjustment. Because remember, the aggregates with Carcy were bone dry just about. But if they weren't, if you had aggregate at Carcy that had moisture in it, you would have to determine the moisture content of it. Okay? So because from past experience, we know that aggregate, sometimes that aggregate's been sitting there for 2 years, especially in the bottom of the bin. 2 years in Carcy. So it's all dried out. So we're assuming then that it is zero, bone dry. So any water that you're adding to it, the absorption, whether it's 2% or 2.3 or 1.9, you're going to get some of that water. So you have to add that water. One group actually forgot to add their adjusted water, and they could barely work it. Okay, they could barely work it. Their slump was so stiff that they had to make their beams and their cylinders. It was tough. Yeah, so you have to include the adjusted water. Because remember, that water doesn't get used up by the hydration process. It's not used for strength development. Okay? So this is pretty straightforward. You've got a blank form. Okay? In Learn. And once I give you the mass of container and concrete, I'll use your mass of container, and you're going to use your previous bucket factor. Okay, or volume of container that you determined when you were doing your density, bulk density of the aggregate. Any questions? Now, this one here again, you can tell you what, if you submit it, I'm just looking to see if I really need it before the next lab. You're going to use it for next week's lab when you're actually calculating. Well, you'll have it anyways. Yeah, give me submit it again. No letter required for this one. We're going to have a letter in the last lab. No letter required. Just give me a brief statement or two saying that, you've adjusted the batch proportions for a trial batch based on 0.1 cubic meters, okay? And the data is attached. So there doesn't have to be much involved. Any questions? So yeah, give me this for next week. So this shouldn't take you too long. Go through the calculations. Like I said, come up with a legitimate slump, come up with a legitimate air content, same with temperature. Okay, this here again, based on your proportions. Okay, 65-35, or if you're using 70-30, or whatever your proportions are, 62-38. Take a guess. Do you think the appearance would look good with that amount of cement? Or do you think it would look rocky? Keep in mind, we got a heck of a lot of cement. We got a lot of paste in our mix. Conrad, you say you don't know. Well, you're designing this mix, right? What should your slump be? How else did you come up with your proportions? Remember, you went through lab 3 where you're doing concrete mix design, okay, by the absolute volume method. You got the City of Winnipeg spec. You know what the temperature should be. Yeah, you follow the City of Winnipeg statement. So again, your slump was what? 70 plus or minus 20, I think? Is that what it said? I can't recall. Go halfway if you want. They went 90 millimeters. Air content, we're designing for 7. Okay, if you're designing for 7% air, what do you want it to be at? 7. I mean, if you want to put 7 in there, fine, but chances are, depending on what you use here, how much you're going to use there. What is there of air 1600 and 1400 state? What does the manufacturer recommend? Okay. I will not penalize you if you set an air content of 4%. Chances are, if you had air content of 4% here on a mix design where you're designing for 7, you did something wrong. Okay? You're designing for 7%. You need 5 to 8. Okay? Concrete temperature. What do you think concrete temperature is going to be? In a lab, is it something that you can control in the lab, Conrad? Minus 40 plus wind chill. Yeah. Well, yeah, you can say room temperature. I mean, your water could be on the cool side because you're going to take it from the faucet. You're going to run a fair amount of it. But you can also adjust water temperature. Okay? But if you took straight water out of the tap, and then you took aggregates that have been sitting in car seat at room temperature, maybe even hotter than room temperature in the summer, in the winter where they're heating the place, 10 to 30 range would work for temperature. Closer probably to 20, not 30, because you're mixing water, okay? CSA actually has temperature criteria that your concrete should be at, depending on the thickness of your structure. If you go through CSA, those 20 tables or 22 tables, at the end of 823.1, we have all those tables. Remember, you looked at the tables for gradations and the exposure conditions. I can't remember what table number it is. But if you have some time, go through all those tables. And there is a section that tells you the thickness, the least thickness of your structure and what concrete temperature should be. And that's because if it's too thick, you're going to want lesser temperatures, your heat of hydration, your thermal expansion, okay? So for a curb, for 150 milliliter barrier curb, the temperature within that can be higher than, say, if you're using a structure that is 5 times as wide, 5 times as high, and whatever, okay? So there's a table. I just can't remember what number it is. I just love the CSA standard. I could read it all night. I need a life, I guess. Anyhow, okay? So come up with typical temperatures that you think that they should be at, okay? Any other questions? Now, these labs, because they're virtual, there's a little bit more onus on interpretation and also a little bit more onus on, and some of you may not have field experience, may not work with concrete. That's understandable. Those of you that come from a concrete background and have done concrete testing, this is probably known at the back of your hand, what the temperature should be. Have you read CW 3310 in its entirety? There's also a table in chapter 9. Yes, that's right, Pavel. Did you also read the City of Winnipeg specification? Like we're looking at it for the mixed design statement, but go through the rest of that spec number, and it talks about concrete, talks about concrete construction, talks about the placement, it talks about vibration, it talks about placement of reinforcement, it talks about a lot of other things. And in there, they'll probably even give you the temperature criteria for concrete to be placed in the field. No. The parameters I will give you, the cylinder parameters next week, because with it, you're going to also get the load. Because next week, if I can go through the videos through WebEx, the YouTube videos through WebEx, without any distortion, I've had problems before. I tried to do a WebEx YouTube video with you guys, and the students could not, they were losing it. It wasn't a video, it ended up being just frames. So I got to try it again. So next week, you're going to get the cylinder information. In other words, diameter and the load. You'll be given that before the lab. So for this lab, all I want you to do is basically convert everything to a 0.1 cubic meter basis. Okay? You're going to determine the yield. You can determine the density. With this afternoon, I'm going to try and, I should get it this afternoon to you, is I'll get you this massive concrete and container. The massive container, the volume of the container you already have. You did that at the density of course aggregate test. Okay? Is that clear? So again, I'll load it up and learn. I'll have lab 1A, massive concrete and container. Boop. Lab 1B, 1C, 2A, 2B, 2C. And I'll give you those values and you'll plug them in. And the rest is essentially based on that. Any questions? Okay, if there's no questions. But you can see in this form here now we have fly ash, water, fine aggregate, coarse aggregate. Cementing materials factors, the mass of cement plus fly ash. Okay, the other example didn't have fly ash, so it was just straight cement. They're talking here cementing materials factor, okay? Kilograms per cubic meter. And again, depending on your yield, here. Now, if I give you this massive concrete and container, I can make it in such a way that you could be way under or way over, right? So I have a little bit of work ahead of me now. I got to look at your mix designs that we've just come up with on a 1 cubic meter basis, the one that you're submitting today, and ensure that when I go through those calculations that you haven't ended up batching 0.3 cubic meters of concrete instead of 0.1. Okay? Because typically this would be what you actually physically determined. You know, you're going to batch those weights. You're going to weigh them out. You're going to put them in a mixer. And it's going to be what it's going to be here. Here I'm going to have to try and come up with a value here for you that makes sense based on your 1 cubic meter mix design, or essentially this one here. Okay. Okay, what does it say here? Fabian, do you take the yield as 0.09 and mass of cement in column 5 for cement factor? Do you take the yield as 0.9 Okay, I want you to go through that calculation. Okay, Fabian? Let me see. I can answer that, but I won't. You have plenty of time now to even check that example and see how they determined the 572.9, okay? I see some comments here already. Good, talk to one another, guys. That's good. How do you calculate that? Well, that's for you guys to find out, okay? I can give you these answers, but you're not gonna benefit anything from it. It'll be quite obvious, I think, once you go through these calculations. Which is your number of batches? Number of T. Okay? Total T is a batch mass, right? And how many of these batches of this weight do you need to make up a cubic meter? That's what it means. Okay? Number of, remember in that example here, let me just go back to that example here. Come on. 214.3 kilograms. That's a batch mass, right? Number of 214.3 kilogram batches per 1 cubic meter. C. Okay. So in other words, 10.7 batches times 214.3 will give you what? Okay. Let's give it some thought on that one. Okay. Does that help you, Conrad? T just stands for total, okay? Anybody got any other questions? Oh, you were just answering Fabian. Okay, sorry. Okay. Okay. If there's nothing else, guys, and everybody's okay with that 10 o'clock submission of labs? Moving it to 10, or did you prefer the 6? I mean, you can always submit it earlier. I mean, I already have a couple labs submitted prior to today, so. Okay, is there anything else? Do you read the water admixtures and fly ash? Okay. Yeah, more flexible. I thought it would. I mean, some people would like to take a break, have supper, and then go back. I originally set that 10 o'clock from a previous lab where they had them on Fridays, and I figured, okay, if you get it to me by Friday, 6 o'clock, you get it before supper, and then your weekend is kind of free. But you guys are on a Tuesday, so it probably doesn't really matter when it's 6 o'clock or 10 o'clock. Okay. I don't want to I can give you more time, but keep in mind, the more flexibility you have sometimes, the tougher it is to try and plan anything because everything's open. And then you leave everything to the last minute. Okay, so you got to have some form of a time frame where things are due. Because remember, when you guys are going to graduate, you're going to be in the workforce. Some of you guys may be closing a tender. And if a tender closes at 4 p.m., it closes at 4 p.m., not 4:01, not 4:02. Has anybody here ever closed a tender and had to submit a tender based on time? Anybody? Okay. Yes. So you know how strictly. What happens, Kelly, if the tender closes at 4 p.m. and you drop it off at 4:02?
It's not valid.
You don't accept it, right?
Nope.
Nope. You know what? I don't know if I mentioned this earlier, but when I was working in the concrete restoration contractor, we would always send 2 guys to deliver a tender, especially City of Winnipeg. You pull up at City of Winnipeg and there's no place to park. So you jump out with the tender, the guy circles the block, and you run up the stairs to deliver the tender. And our clocks in our office and our wristwatches were set to the City of Winnipeg clock at the tender desk. Because even though their clock could be 5 minutes faster than, say, the actual time, and you could be set to the actual time, their time governs. So if you deliver it at 4:02 and you look at your watch and you say, oh, I still got 3 minutes, okay? And it's 4:02 on their clock, and it is actually 3 minutes to 4 on yours, which is the correct time, tough apples. Their clock governs. And it's 4:02, it's late, they don't even open it. They'll just hand it back to you and say, not accepted. So get used to deadlines, because when it comes to tenders, when the tender closes at a certain time, it closes at a certain time. And any excuse you have, well, the traffic was bad, I couldn't find parking, tough apples, they don't care.
A lot of the contractors know how strict the city is, and they make sure that most of their tenders are in on time because, yeah, they aren't flexible whatsoever. They're just wanting to get the work out and done. So,
well, really, whether you're government or private, you should never be flexible, because 4 o'clock is 4 o'clock, or whatever the time, 12 o'clock or 12 o'clock, whatever. The time set is the time set. And whether it's a private, once you're tendering, you should never allow to exceed the time. Because if you do it for one, you got to do it for all. Okay? If you send one 5 minutes, the other guy says, well, I was rushed. If I would have had an extra 5 minutes, I could have adjusted my prices to be lower. I lost. I'm now number 2. Okay, so look them up with every other excuse. I used to submit tenders. I'd run with my tender in an open envelope. And my boss would say, John, before you walk in, give me a call. I'd be sitting in the car. And he'd say, okay, John, change these numbers. I did some more number crunching. I think we gotta come down on this price. And that's bad because that's where you can make a mistake. So I would physically open the tender. Well, it wasn't sealed yet. Scratch out the price that we had typed in. I'd write it in freehand. Boss wanted a lower price, and I'd initial it. Then I'd seal it up and then deliver it. So that's how some close contractors work. And a lot of them are also scared that if you deliver your tender a day in advance, that your price is going to leak out to somebody. I don't know how, but they do. And for some reason, contractors do not like to put a tender price in a good 1 day in advance or 2 days in advance. They always wait for the last minute. Anyhow, yeah, horror stories. There's all kinds of those. But it's deadlines. They're there for a reason. So hopefully these deadlines and all your assignments and all your projects give you good training for what the real world's going to be like out there. Especially if you get into a lot of estimating and tendering. Okay. Anything else? Everybody's good? There's no questions. It's already 11:22, so now we're all ready. Okay. Again, if you have any questions, again, just reach me by email. Okay. Have a good one, guys. Take care. Welcome, guys. Everything okay, Sean? Emmanuel? Mitchell? Anyhow, you know how to reach me if you need anything.